right, so this is problems 30 through 40. Consider, and this is number 30 of the death packet. So consider the 3 points, 4, 33, 5, 27, etc. Given any straight line, we can calculate the sum of the squares of the 3 vertical distances. Whoa, what is that? 3 vertical distances. The 3 vertical distance from these points to the line is known as the residuals. So they want me to calculate the residuals, but they want the sum of the squares, so they want the squares of the residuals. So they want the residual squared. The vertical distance is the residual, but they want the sum of the squares, so they want the residual squared. What is the smallest possible value this sum can be? Well, the smallest possible value is going to be based on the least squared prediction line. So we basically need to calculate, we need to come up with our regression equation. So I've taken a moment and I entered the data into L1 and L2. So here's all my X values, 4, 5, and 6. Then I have 33, 27, and 15 for my Y values. And I'm going to go ahead and run a regression on this. I'm going to go stat, test, linear regression, t-test. And I'm going to store my equation into Y1, so alpha trace. And so there's my regression equation. Well, I don't really care about that. What I care about are the residuals. So now that I have that, now that I've done the regression equation, I can go back over to stat edit, and I'm going to go over to L3, and I'm going to go to the top of it, and I'm going to calculate my residuals. All right? So to calculate your residuals, you're going to go second stat, because you're looking for the list. And your calculator is going to show up differently depending on what all you've put in your calculator. And I scroll down, and there's resid. And so that's going to give me my residuals, because resid happens to be short for residuals. I know that's a surprise. And I'm going to press enter, and there's my residuals. Well, if I sum those up, they sum to 0, because the sum of the residuals is always 0. But they ask for the sum of the squares. So I can go -1 squared. So I'm going to go -1 squared plus 2 squared plus -1 squared. And when I sum those up, this is going to be 1 plus 4 plus 1. And there's a way to have the calculator do that for you, but not that big of a deal to do it here. All right. So that so the answer for B for this one is B. And if you got questions about that, give me just a second. So the basic question was, hey, can you show me how to calculate the residuals again? So I've already entered the data, the X and Y data. So I'm going to go stat test, and I'm going to run the regression equation. So I've gone all the way to linear regression. I run it. Make sure you do an alpha trace for make sure it stores it into Y1. Has to be stored. Now that that's done, I'm going to leave, and I'm going to go to stat edit, and I'm going to go up to the top of column L3. And I'm going to press the second button, and where it says stat, right above it, it says list. And I'll scroll down to the word residual. And I don't know where it's going to show up on yours. And press enter, and then it populates the residuals. Now I'll say this real quickly. If residuals did not populate on your calculator, all right, that means you probably have stat diagnostics turned off. So here's what you need to do. You need to go to mode, and you're going to scroll all the way down till you see stat diagnostics, and make sure stat diagnostics on. If it doesn't pop, and then redo the thing again. All right. All right, so we're looking at page number 31. Studies made relating power of auto batteries as a function of price. Data from the sample of 13 batteries generates the following computer output. Which of the following gives a 90% confidence interval for the slope of the regression line? So first off, this right here, here's my Y, the constant tells me my Y-intercept. So y hat equals 410.997 plus, this is my slope, 5.5297, and price is my x variable. All right. And by the way, I could have, instead of putting y hat, I could have said power and written power there. But that's not what it asks for. It asks for the 90% confidence interval for the slope. Well, we've identified the slope as 5.5297, so that gets rid of A and B because those are based on the y-intercept. And our equation for the confidence interval is B, which is our sample slope, plus or minus T star times SB. Well, B is the 5.5297 plus or minus. We'll come back to T star in just a second. And since we're dealing with slope, we need to only be looking at the slope line. This is my SB. This is my standard error of the slope. So this is going to be 1.135. So that gets rid of C. So now I need to calculate my T star. Well, remember, I need to know my degrees of freedom. Degrees of freedom is n minus 2. And in this case, they told us that it was 13. Now, I'll be cruel, and I may not tell you that, but it's also the one written right there on the residuals. So on the residual line, you can also find your degrees of freedom, okay? So in this case, 13 minus 2 is 11. So we need to do a 90%, what was that? Yes, 90%. So here we go. Second bars, inverse T, parenthesis 1 minus 0.90 divided by 2, and our degrees of freedom was 13 minus 2, or just 11. And we end up getting a T star of 1.7958. All right, 1.7958. Which makes E my answer for 31. All right, number 32, suppose the correlation is negative. Given 2 points from the scatter plot, which of the following is possible? All right, so we have a negative trend, but we have a scatter plot. And let's just say that's my trend line. The first point has a larger X value and a smaller Y value. Well, what if this point wasn't there and this was my first one? I have no idea what's going to show up on the scatter plot because I could just as easily had data points that went like this. That's still a negative trend, but we swapped the order of the data points. Because it's a scatter plot, the data is scattered. All right, we don't know which one's coming first and which is coming next. We don't know because it's scattered, it's random. All right, some are going to be above, some are going to be below, and we don't know what order they're going to come up in. And because we don't know the order that they're coming up in, all three of these are possible because it's a scatter plot. Number 33, a regression analysis on the relationship between the average annual profits and millions of dollars of insurance companies and the yearly number of major natural disasters, et cetera, gives the following computer output. If the analysis was rerun using the number of disasters as the dependent variable instead of profits, what would be the correlation coefficient? All right. So in other words, they're saying, hey, if you swap it, what would happen? Guess what? The correlation is going to be the same. It doesn't matter the order. So we just need to calculate the correlation coefficient. Well, how do we do that? Well, we know R squared, and we never use this for this course. R squared adjusted is something else. We don't work with it. We know R squared equals 0.465. So I'm going to take the square root of R squared, 0.465, and raise it to the half power. And I end up getting 0.682. All right, so we're dealing with a 0.682, which gets rid of A, B, and C. So we're looking at D and E. So I need to check to see what my slope is. My slope is negative. This is negative. All right. And you're like, well, wait a second. We swapped them. Doesn't matter. It doesn't matter. Swapping them isn't going to change it. Now, what will change it is let's just say I had a negative change in Y over a change in X. If I multiplied either one of the X's or the Y's by -1, it'll change the direction. So if I multiply this by -1, it changes it. If I multiply the denominator by -1, it changes it. But what I have, doesn't matter which one I put in the numerator, which one I put in the denominator, the correlation remains the same, okay? So 33 is E. All right, number 34, which is the correct scatter plot for the computer output to the right? Well, they're telling me this is my y-intercept. So my equation is going to be y hat equals 10.3 minus 1.7 x. And I know I rounded that off, but that's close enough, all right? So y hat equals 10.3. So that means I need to be starting at 10. So that gets rid of this one. That gets rid of this one. And this one as well. So these two are starting at 10, okay? And so then I need to sit there and go, well, what do I have? I have a very loose correlation here and a very strong correlation here. I know this is strong because the data points are close. Right here, the data points are not that close. So with that said, let's look at my R squared. My R squared is pretty strong, but we should really be looking at the correlation coefficient. And my correlation coefficient is going to be the square root of 0.906. .95, and remember this is negative, so this is a negative 0.95. And when I look at this and I go, you know what? Data is pretty close to that line. This one is pretty far away. It's not this one because the data is not that close. This one's the one that has the strong R. This is a strong linear relationship. This is a weak linear relationship. So my best answer to this one is C. A linear regression, number 35, a linear regression analysis performed on two variables. Which of the following tells you that another model is probably a better fit? Okay, so the first thing I always look for is if the residual plot has a pattern. The next thing I would look for is to see if the scatter plot is nonlinear. In this case, they tell me the residual plot has a pattern, so that's my best case. This is what I'm looking for. Residual plot has a pattern. Some other models better. If the scatter plot is nonlinear, some other model will be better, but this is what I look for first. First is the residual plot have a pattern. Second is whether or not the scatter plot is nonlinear. All right, number 36. This is a challenging problem actually, which is the correct regression output for the scatter plot below. And first off, we have a negative slope and we have a constant. We're going to have a negative slope. So we need to make sure that our slopes are negative. Well, this one has a negative slope and it's starting at 0.5. At a 5, that looks good. This has a net starting at a y-intercept of -5. That's wrong. This is starting at 5. That's good, a y-intercept of 5, but has a positive slope, so C is gone. This is starting at 5 and has a negative slope, so this is a possibility. And this is starting at 5, but has a positive slope, so it's gone. So we've narrowed it down to D and A, all right? Oh, D and A, how about that? So the question is, which one is the appropriate response? Well, if I drew a best fit line, I know that's not very straight, but let's just say it were. Let's just say it's a good straight line, something like that. Like, gosh, that's actually pretty linear. That's a pretty linear relationship, and it's reasonably strong. That's a reasonably strong linear relationship. So let's take a look at these. And in this case, I have an R squared of 0.765. So I'm going to take the square root of that, 0.765, raise it to the half power, and I end up getting 0.87. The slope is negative, so this will be a negative R. So my R is negative, but anytime we have a 0.87, that's a pretty strong one. Whereas if I look down at D, I have an R squared of 36.5. And so I take the square root of 0.365. And I end up getting 0.6. And that's moderately strong. So I have a strong one here and a moderately strong one there. And I'm going to say this is pretty, on average, this is a fairly strong linear relationship. All right. Now I get that it's difficult to tell whether or not, because we don't work with enough data. So they go, hey, how do I know for sure if it's strong or not? So you're going to need to tell me, you're going to need to trust that this one is this particular pattern is pretty strong. So because this is strong, this is going to be A. D is not bad, but it's just not strong enough. All right. The R 0.6 is not reflective as how close the data points are to the line, or how predictive that equation is. All right, number 37, automobile insurance company is interested in the association between age of SUVs and odometer readings for their clients. Data from 20 randomly selected clients generates the following computer output. Which of the following gives a 96% confidence interval for the slope of the regression line? Slope of the regression line is going to be plus or minus T star times SB. And remember, we need to know degrees of freedom is n minus 2. In this case, 20 minus 2, or degrees of freedom, are 18, which is the same thing that shows up here in our residuals. Our constant, our y-intercept is here. That's not what we're looking for. We're looking for the thing below it. So this is my slope. So 115,675.2 plus or minus. We need to stay on the slope line. So this value right there is going to be my SB, or my standard error of the slope. So I'm going to come back to T star in just a moment. And SB is going to be 1,678. And I need to go ahead and calculate my T star at this point. So second vars, inverse T, parenthesis 1 minus, I said 96, yes, 0.96 divided by 2. Degrees of freedom is 18, or 20 minus 2. And I get 2.214, which in this case means that E is my answer. All right. All right. Number 38. A theater owner believes that attendance actually goes up if the best seats are advertised for higher prices below the computer printer output. What is the p-value for a t-test with beta equals 0 and beta greater than 0? So notice everything we've done in class has been a not equal. All right. And this one is also run as a not equal to. Now you're going, how do you know that? I'm going, well, they always do. But in the event that you're like, hey, I don't trust it, let me show you how to check. Because this is kind of cool, I think. Our t statistic is centered at 0. And we have 2.48. That is our t value. All right. So let's go back. And we have 6 degrees of freedom. All right, we have 6 degrees of freedom. So let's go to a TCDF. Second vars, TCDF, lower bound, because we're interested in going this way, is 2.48. Upper bound, infinity, Degrees of freedom happen to be 6. So that means my sample size must have been 8. And what do I get? I end up getting a p-value of 0.0239. I end up getting a p-value of 0.0239. So a greater than value is going to be 0.0239, and that's what they asked for. And if it had been two-tail, we just multiply it by 2. All right, remember when you go from one tail to two tail, so if you went from this, a greater than, to a not equal, and everything we've done in class has been based on a not equal. If we go from a one tail to two tail, you double it. All right, and that's what they did here, is they actually ran a two-tail test. The reason being, they're just saying that this is equal distance right here, negative 2.48. But this would be the not equal version of that. So question was, hey, why again was it B as opposed to C? Well, the reason it's B is they only asked for it to be greater than. So that means I'm only looking for this part of it. So I'll scratch that out. So basically what they're saying is they have 0 and they want 2.38. So they only want the greater than direction. So they're only looking for that direction. In that direction, 2.38 has that p-value of 0.0249. Had they, so greater than is this way, not equal to is C. So this is the greater than one, and this would be the not equal version of the same answer. Number 39, below is the computer output for regression analysis. What is the equation for the least squares regression line? So first off, the very first thing I do is I look for either it'll say constant or intercept. Here it says constant, regardless whether it says constant or intercept. This is my y-intercept. So y hat equals negative 0.73391. And then whatever's below it is my x variable. So in this case, and this, that making this my slope row, and this is my x. So, and it's positive, plus 11.8204x. Now, one of the really cool things about this is you can write it like this, but then you have to define x and y. On the other hand, I can come back and go, you know what? 8204. They told me right here by putting that label there that this is x. So GPA is my x. And I know I have a negative 0.73391. So what's my y hat? My y hat is the other thing, which in this case is starting salary, because those are my two variables. All right. So starting salary. And if you write starting salary with a y hat equals negative 0.73391 plus 11.8204 GPA, and you write your equation like this, you don't even have to define your y and x. Now, I think you should. I think it's risky not to, but they're very, very happy with that type. They like it when it's written like this. They think you know something. All right. And I sometimes the questions, just being truthful with you guys, listen to this very carefully if you're virtual, or if you're listening to this on video, sometimes it's hard to tell what the x and y variable is, but they actually tell you. Whatever that is your x every single time. So even if it's difficult to know which is one that you're using for your, what's the independent or dependent, if it's here, that is your independent variable, that is your x, and it will be every single time. Before Challenger went off at 31 degrees Fahrenheit, each of the 23 launches experienced from 0 to 3 O-ring failures. There was some speculation that the number of O-ring failures was related to the temperature at liftoff. A computer printout performed too late is shown below. All right. Is there a relationship between the failure and temperature? Well, basically at that point, I need to go, you know what? Is it predictive? So what is my value? All right. Well, my p-value happens to be 0.0052. And it's like, okay, so there is evidence of a relationship, all right? And when I say there's of a relationship, they're saying, are they correlated, all right? And because we have X and Y variables, X and Y, are X and Y related? So is the slope, is the slope valid? If there is no relationship, we're going to have a p-value. We're going to not have a p-value. We would say that our slope, our beta 1 equals 0. And there is no linear relationship. But in this case, we have a very small p-value. So we're like, yeah, there's a relationship. How significant is the relationship? Well, we normally work with alphas at 0.05, 0.01, and they're going to take 1 out here. Then I notice they have 0.001. So where does 0.0052 go? Well, it's definitely smaller than this. It is. I should have put these in different order. Should have gone at least to greatest. Sorry about that. Let me change that. So I have 0.001, then I have 0.01, and then I have 0.05. And I'm going to make these all the same length, all 4 places. Well, 52 is definitely less than 500. 52 is definitely less than 100, but 52 is not less than 10, so it's in between here. So the 0.0052 lies in this interval. So there's evidence of a relationship at the 0.01 level. In other words, I would reject the null at alpha equal 0.01, but I would not reject the null at 0.001. 0.0052 is greater than 0.0010, oops, 0.0010, 0.0052 is less than 0.010. So here I failed to reject, here I would reject. So there's evidence at the 0.01, but not at the 0.02 or 0.001. I think I stumbled on my words there, so I may have confused you.